All right, so now we begin a new part of the course. So let me just contrast this with what we had before. So before, we were solving this system, right? We had AX equals B system. Now, B could be 0. And by the way, what's that system called when B is 0? We use the term. I mean, it's not important to just memorize that term or anything like that, but those are called homogeneous systems, right? When you have AX equals B system, AX equals 0 systems. This is a homogeneous system of equations. Okay. A itself is a matrix whose dimensions could be square, but not necessarily. You could have a situation like this, where matrix A is a rectangular matrix. Then it multiplies vectors that are tall. Anyway, it applies to only those vectors whose number of components is exactly the same as the number of columns of A. That's when the matrix times this X is defined. And out comes a vector B that is as tall as the number of rows that A has. Okay, so that was situation 1. You also had situation 2, where you may have had like a tall matrix A, and that tall matrix A multiplied short vectors X, and out come the tall vectors B. Okay, these are cases with rectangular matrices. And then you had the cases that we actually started with, when the matrices were square, okay, and the dimensions of the vectors to which it was applied, and those which came out on the other end were the same. Okay, the number of components in those vectors is exactly the same as the number of rows that A had, which was the same as the number of columns that A had. Okay. Okay, so the question is this: what are the conditions? What kind of matrix does A have to be for there to be a non-zero solution to the system AX equals B? Okay, when does this system of equations have a non-zero solution? So can somebody help me out? When did you get, like, in a homework question, let's say you have some A in class, you had a situation where you row reduced A to something that looked very simple, so the row reduced form, and then on the other side you had the right hand side, you had exactly the solution that you read. So you row reduced A to an identity matrix if the matrix was nice, and if B on the other side was something, then that AX equals B had a unique solution. And if when you row reduced a square A and you got an identity matrix as a result of those row reductions, Gaussian row reductions, and if the system that you were solving was AX equals 0, then that system had a single unique solution, X equals 0. Okay, but the row reductions could have led you to a matrix which was such that the solution to the original AX equals 0 system was something non-trivial. And by non-trivial, we mean non-zero solutions to the AX equals 0 system of linear equations, right? When did that happen during Gaussian elimination?
Didn't that happen when one of the rows was completely 0?
Yes, exactly right.
Elimination?
Yes, exactly right. So when you got one of those zeros, one of those vectors that was a 0, so there's someone coming in, I have to admit. Okay, right? So then the system had a non-trivial solution, some non-zero vector that was in the null space of A. This was the question of solving for the null space of A. Okay, solving for the null space of A. That's what we did. AX equals 0 is to solve for the null space of A. And for certain matrices in the null space of A, there is something other than the 0 vector. That was the main point. So now we're going to be solving a new problem, and all the matrices, all A's, are square now from now on. Okay, and the new problem. So before it was AX equals B, so that was the problem before. And now the new problem is AX equals lambda X. And first, we'll spend some time actually parsing what this means today, the first like third of the lecture or so. And then we'll have a streamlined way of solving, so to speak, this system of equations. Okay, so notice what we have here is that on this side, we have matrix times A times a vector. Vector is X. A is applied to X. The story is the same throughout. So A, you think a linear transformation. A is applied to X. Out comes something. In this case, AX. And here, you want that AX that comes out on the other side to be a number times X. So lambda stands for a number. So don't let this lambda confuse you. Okay, it's just a notation that's conventionally used throughout. Lambda is just a number. There's nothing special about lambda. Well, we'll say it's actually very special, but other than it's, it's just a number. Okay, so here you have number times vector, a vector. Okay, so what does this equation say? First, let's think about this geometrically to begin with. And I'll draw a few pictures. Let me add some new pages here. We'll need a couple because I'll be writing throughout. Okay, so what this says is, again, A is a transformation, A is applied to X, something comes out on the other side. Whatever that other side is, whatever comes out on the other side, you want that to be a multiple of the X that came in, that X to which A was applied. So A takes in X, out comes AX, right? So whatever comes out on the other side, if it is some stretched version of the original vector that went in, then that kind of vector we're going to call an eigenvector. So those vectors X that solve this system of equations are called eigenvectors. X is an eigenvector. Eigenvector here. Okay, this X here is an eigenvector. And lambda is an eigenvalue. In fact, eigenvalues have those. We'll see how to find the eigenvalues for a matrix, and those eigenvalues will have associated eigenvectors. So lambda is an eigenvalue. Okay, so let's draw a couple of pictures first. Okay, so here you have an R2. Okay, so you have R2, and let's suppose that this is some vector in R2. So this looks like some vector that is like maybe like 3, 1 or something like that, this vector. Okay, when A is applied to it, so this is R2, and this is the domain of A, and these are the images, codomain of A. Okay, so here I have another version. Let's draw it in a different line, as blue. Okay, so here's the codomain. So again, A acts on the vectors in this R2 on the left, and out come the blue vectors. So in particular, this vector, in general, vectors will change direction. So this vector 3, 1, to which A is applied, may come out on the other side as a vector like, I don't know, like this. See, A is applied to it, and out comes something like 1 minus 4, or something like this. Let's make this A times, let's say 3, 1. Maybe that's the kind of linear transformation it is, that when it's applied to this vector, 3, 1 vector, out comes that particular vector. Okay. Maybe here's another vector, like maybe this vector here. Okay, so this looks like minus 2, 5, 4, maybe. It's minus 2, 4, about. And out comes maybe something like this. Okay, so when A is applied to minus 2, 4, out comes this blue vector that looks to me like minus 5, something like 2, maybe, whatever. Okay. In general, this is what will happen. You apply a transformation to a vector X, it will change direction, will point in a different direction. But there are some special vectors, call them V, that are the eigenvectors. These are the eigenvectors that I talked about here that do not change direction. This purple, this is, suppose, I don't know, there is some vector here. Maybe it looks like 2, 3 or something like that. Okay. that it doesn't change direction. When it comes out on the other side, it may stretch, but it doesn't change direction. So maybe it comes out to something like 4, 6. Okay, this 4, 6 is the result of applying A to the original vector 2, 3. Okay, so 2, 3, 2, 3, the purple guys are special. And out comes 4, 6, which simply happens to be a stretched version of the vector that went in. So this is exactly twice 2, 3. This guy too, the stretch factor, is called lambda. Okay, just using the screen, you can use any letter that makes you happy in principle, but using the letter lambda is just a convention and we'll follow it. So here we have a situation where for this particular vector, which is a very special vector indeed, in that in general, all vectors change directions, but some vectors stay put on their own lines, and those vectors are the eigenvectors. So this is the eigenvalue associated with 4, 4, 6. Okay, with 2, 3, or 4, 6 is also an eigenvector with 2, 3. If I looked at 4, 6 here, that would go to 8, 12 here somewhere. Okay, that would also be stretched twice under this linear transformation. But any vector here, any vector on this line is an eigenvector, and all eigenvector. And all those vectors in that purple line have this associated lambda 2, which means that all of them get stretched twice. Okay, so 4, 6 vector, for example, gets taken to 8, 12 vector. It gets stretched twice. Now, in general, like as I draw these pictures as we go along, it's kind of normal to have both of these, the domain and codomain, be drawn on the same R2 plane, just like this. Okay, just to see that this purple lines, the purple vectors line up exactly on their own lines, and all the other vectors change direction. Okay, so this is the geometric view of what eigenvectors and eigenvalues are, and we'll keep the geometric view in our minds as we continue with our examples that are coming throughout the day. And we'll see our next goal is to look at the streamlined way of computing the eigenvalues and eigenvectors for, in general, n by n matrix. So here's the same picture in one of the slides. This is also in the reading assignment, same picture. So in this particular picture, for example, here's the blue vector that changed its direction. So the red vectors are in the codomain. The blue vectors are the ones that go in. They all change direction, except for those guys that are on the green line here. Those on the green line, they get stretched twice. Those are the eigenvectors. And the factor by which they get stretched, 2 in this case, is the lambda. Any questions so far about what the problem is about? This is the setup of the eigenvalue problem. It's unimaginable how many applications this need of finding, in how many places this need to find the eigenvalues and eigenvectors of a matrix show up. Okay, well, maybe if we have time, we'll talk about that. We can talk about that endlessly. And in fact, if you take any other course in mathematics or applied mathematics, the eigenvector and eigenvalue problem will come up, okay, in almost every follow-up course. If you're taking like calculus 3 or 2, maybe even, they come up there. And certainly in other places. Okay, so now enough of that. Now, is it clear? Are there any questions so far about the setup itself? Now, I want to give you an algorithm for computing eigenvalues and eigenvectors. But first, as we always do, let's just, for a few matrices, you can just guess by thinking about the action of those matrices. What are those matrices all about? What do they stand for? Simply guess what their eigenvalues and eigenvectors will be. So let me start with a couple of small such matrices, and then we'll do an example. First of all, just before we even do one of those immediate examples, so let me give you one more example of an eigenvector of an eigenvalue just for a given matrix that I will use, that I used in the other section. I wrote it down here somewhere, which is, what did I use? This one, 1, 2, 5, 4 matrix. It's some matrix A. Okay, So now I'm not asking you what the eigenvalues and eigenvectors of this are, because it may not be immediately obvious what they are, and we'll see how to compute them. But if I told you an eigenvector, given the definition that we have now in place, we can check whether it's an eigenvector or an eigenvalue. So here's my claim, and here we'll just simply check. Claim 2, 5 is an eigenvector of A. Okay, check. Indeed, A times X. So what does have to happen for this vector to be an eigenvector of A? One, it must end up being a multiple of itself on the other side. So now I'm going to apply A to X. So here's my A. Here's 1, 2, 5, 4. And now I'm going to apply it to this vector. So this is my A, this is my X, to 2, 5. Okay, let's compute it. Well, what comes out on the other side? Okay, 1 times 2 plus 2 times 5.
It's 12.
It's 12. And here's 5 times 2 plus 4 times 5.
30.
It's 30. Okay, is it the same as 6 times 6 is just a number, lambda is just a number. 6 times 2, 5. This is indeed lambda times the original vector. So yes, the check works out perfectly fine. 2, 5 happens to be an eigenvector. Now, is 4, 10 an eigenvector? Yes, that guy will also be stretched 6 times. How about the vector that's 20, 50? Yeah, that will be stretched also 6 times. Okay, any vector that is in fact a multiple of 2, 5 will be an eigenvector. Anything that lies on the line on which the vector 2, 5 lies will be an eigenvector, because when you apply A to any of those vectors, out come 6 times those vectors on the other side. There's no other thing that can happen here. So this is indeed the case. Okay, so now if someone were to give you this matrix, and if you didn't know how to compute eigenvalues and eigenvectors, maybe you wouldn't guess immediately what the eigenvectors and eigenvalues were. But for some matrices, you can actually guess. And let me make that point. Okay, so let's take this matrix 0, 1, and 1, 0. And actually, in this section, I'm going to denote it by R. I always denote matrices by A, but let's call this R. The reason I use R here, this section, is because it will turn out this is called a reflection matrix. Reflection matrix. Why is it called a reflection matrix? Well, it's a linear transformation, right? So let's think about what it does. So here's my R2 plane. So this is the R2 plane. Okay. And let's think what Rx does. Okay. So suppose I apply R, the vector that goes in is any vector like x1, x2. Okay, so let's take a concrete example here. So if you let, for example, something like, I don't know, 3, 4 go in, what comes out on the other side? What's the?
Would be 4, 3.
Yeah, 4, 3 comes out on the other side, right? This is, by the way, one of those elementary matrices that flips the rows. So it's applied to a matrix that is a vector, 2 by 1 vector, and it flips its rows. So it changes the coordinates. So the effect of this matrix is to flip the coordinates. Well, what does this mean geometrically? Well, let's take a look at a vector like, I don't know, 2, 5. What would it do? Well, let's take 5, 2. 1, 2, 3, 4, 5, 2. Okay, what will it do to this vector? This vector here is 5, 2. Where will it take?
To 2, 5.
It will take to 2, 5 here. This vector is 2, 5, which is equal to A times 5, 2. To A times 5, 2. Okay, that's 2, 5. So let me just draw it here. So that's the result. Do you see what does it mean to change the coordinates of a vector? It means to just reflect this across the 45-degree line. So here's a 45-degree line. you give this vector something like, I don't know, like, well, what happens if you give it some other vector? Like, for example, like, I don't know, let's take this one. Looks like -1, and this looks like 1, 2, 3, 4, -1, 5. Where does it minus -2, well, -1, -5? Where does that one go? It flips the coordinates, right? So it will go somewhere here. What am I doing? What am I doing? It will go somewhere here, which will be -5, -1, okay, which is the same as -1, -5 when A is applied to it. When A is applied to it, you get this vector out. So again, it's reflected around this 45-degree line, right? That's why it's called the reflection matrix. Now to the main question. Okay, so what are the eigenvectors? Can you name an eigenvector? So by the way, the procedure we'll first find the eigenvalues, and each eigenvalue will have an associated eigenvector. But here we can guess the eigenvectors exactly, immediately. Okay. Can somebody help me out?
Would it just be like 1-1? Oh, sorry.
Yeah. 1, 1, 1. It would be one of them. Okay, anything in this line. Okay, so anything in this line. So here's 1, 1. 1, 1 is an eigenvector. Because when you apply A to this 1, 1, it stays put. It flips the coordinates, but the coordinates are the same. So the bottom one becomes the top one, and the top one becomes the bottom one. But the point is that it's 1 times itself. So what's the eigenvalue? The stretch factor. I'm sorry?
Infinite?
Yeah, it's 1, right? Eigenvalue 1. Okay. All right, so we found an eigenvalue and an associated eigenvector. So one eigenvalue is 1, and its associated eigenvector is 1, 1, for example, or 20, 20, or -2, -2. Any vector on this blue line is an eigenvector. In fact, the blue line is called the eigenspace. Maybe we'll denote it by eigenspace associated with the eigenvalue 1. Okay, the span of all these vectors that lie on that space, all the multiples of that blue vector on the screen. Okay, are there any other eigenvectors?
So if it's on blue line, is it gonna be like infinite?
Yes, an infinite number of, correct, yes, an infinite number of, yes, the number of eigenvectors is always infinite. Yes, correct. Any multiple of that blue vector. But what are other, so I guess, okay, my question wasn't precise. What I meant to ask it was the following. Are there any eigenvectors that do not lie on the 45-degree line?
Is there another one where it's like -1 and 1?
Okay, so what happens to -1, 1? Let's take the one that let's make that one purple, maybe. Purple. Did you say -1, 1? It is an
Yeah.
eigen. So -1, 1. Okay. So what happens? Okay, so let's write down what happens to it. It reflects it also, right? So reflections is the thing. So it changes, it makes it 1 - 1. So it makes it point in the opposite direction. But the point is that the vector stays on the same line, right? You take -10, 10, it will be reflected to 10 - 10. Will point in the opposite direction, but will stay on the purple line. Okay, so let's call this a 135-degree line. This is an eigenspace as well. What's the eigenvalue associated with it?
-1.
-1 times the original vector. So this is -1, 1 is the one that you've suggested as x. This is the same as lambda x. So I want the same x on this side. And of course, my matrix is the same. That's the reflection matrix. So anything on the 135-degree line is also an eigenvector. In fact, let's give this guy a name. This will have, because its eigenvalue is -1, let's call this the eigenspace associated with the eigenvalue -1, right? So now I have two spaces, two one-dimensional subspaces of R2, okay, two lines in R2 that give me the eigenvectors. Okay, anything on those two lines are the eigenvectors. The ones on the blue line are associated with the eigenvalue 1, and the ones on the purple line are all the eigenvectors associated with the eigenvalue -1. Okay, so it's clear with this example what's happening, right? These are the eigenvectors and eigenvalues. And we didn't use any procedure or anything to find them. We guessed them, and they turned out to be correct. And we guessed them by thinking about the action of A, by the geometric meaning about the geometric meaning of what A does as a linear transformation. Okay, that's great. It's a good example. Now let's move on to actually ways of finding eigenvalues and eigenvectors. Okay, so well, actually, let me ask you one more. What's the eigenvalues and eigenvectors of the identity matrix? Let's make it a 3 by 3 this time, so we have a bunch of zeros. What are the eigenvalues and eigenvectors of this? So it's applied to some vector, some multiple of it should come out on the other side. Which vectors are such that when I is applied to them, a multiple of it comes out on the other side?
Any vector in R3?
Exactly. Any vector you take in R3, when the identity is applied to it, that vector stays put. It doesn't even stretch. And that's any vector in R3. So any vector is an eigenvector. Any V of R3 is an eigenvector. What's the eigenvalue associated with the vector that's an eigenvector?
1?
Yeah, is an eigenvector. And vector for lambda equals 1 with it. Okay, all right, now let's move on to the concrete examples. Okay, example 1. Example 1. Find eigenvalues and eigenvectors for this matrix. The one that we used, which one was it? Blah, 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 blah. It was 1, 2, 5, 4. I want to find the eigenvalues and eigenvectors of this. We actually, okay, so we checked whether one of those was an eigenvalue and eigenvector. So it turned out that 6 was an eigenvalue and 2, 5 was an eigenvector, if I'm not mistaken. So now we're actually going to describe a procedure of finding them in a methodical way. So this procedure can be used in any n by n matrix. Let me ask you this. Oh, I should tell you about something. So before we get to this example 1, I want to tell you something, one more thing. And that one more thing is this. Is making sense of A equals, again, we started with this really, AX equals lambda X, and we kind of understand it geometrically what this is saying. But for the procedure that we're about to describe, we really want to have this in matrix form. So first, before we go to that example, this is, again, matrix times vector. And this is, again, number times vector. I want to rewrite this as matrix times vector. Which this side will be the same, AX. And the other side will also, I want to have matrix times vector, right? This other side, matrix times vector. And why am I doing this? Okay, it will be clear in a second, but first let's think how we can rewrite this that way. So let's take this example, 1, 2, 5, 4, since we're sticking with that matrix. And let me write down this AX here, the usual way, X1, X2. And on the other hand, I want to have this lambda times X1, lambda times X2, right? This is what I want to have. This is my lambda X. Now, here's the claim. This is the same as I'm going to rewrite the left-hand side here. And the right-hand side, I'm going to make a matrix. And how do I make it a matrix? Well, I'm going to involve an identity. I'm going to, first of all, as a matrix equation, if I wrote this down as this, like x1, x2, no one will object that the top line, that this line is exactly the same as this line, right? Everyone agrees. And this is also the same as, where's my paste? There's no paste. Okay. Let me try to copy it one more time. And this is the same, just another way of writing this down, as I'm going to take this to this side. So I'm going to make this a minus sign and actually take lambda out. So I'm going to put lambda here, and these guys are going to be ones then, right? So nothing has changed. And so I took this, both of this to the left-hand side, so I end up with this. Do people agree? So now I have AX minus lambda times the identity matrix times X equaling the zero vector, right? Do people agree that that's what I have? It's just exactly the same way. I can even factor that X out. So one more step here is that I'm going to do is the following. I'm going to take this guy, okay, and make one tiny modification to it. And that tiny modification is going to be that I'm going to just take this outside the brackets, right? That's the only thing. Okay, it's the same thing, right? I didn't do anything. Do people agree? It's the same thing. And now I have an expression. Let me erase this actually and put it like this. This is how I got here. This is the next step. These are all just what I'm doing here is just rewriting the original system of equations. And why am I doing this? Okay, just give me a second. So a minus lambda I times x equals 0. Okay, this is why I'm doing it, because this expression now I'm going to start using to good effect, very productive effect. Okay, so I'm going to copy this. So what I want to say that so are people good with this right now, what I wrote here? So it's just a way of rewriting the original equation, AX equals lambda x, which is this. This is AX equals lambda x here, is the same as this. Okay, this is the whole point of this little scratch paper here of this slide, whatever you might call it, is to show that these two ways are refer to the same thing. Okay, it's just a different way of writing down the same thing. It's just this one is in the matrix form. It involves this identity matrix. Do people have any questions about this? Because this is kind of a key step. Like in my experience and other people's experience, if there's some confusion initially with the eigenvalue and eigenvector stuff, it comes from this, like understanding this way of writing it down. So I just want to make sure I stress this fact, that these two ways of writing down the same problem are equivalent, right? Make sense? Okay, so in this particular example here, okay, so again, this is, so we solve, find eigenstuff for that. Solution. So we need to solve AX equals lambda x for lambda and x. And that's another source of confusion. First time I saw this, or most people see this. Okay, so somebody's asking you to solve AX equals lambda x, and they're telling you you don't know x and you don't know lambda. In fact, the first time I saw it, it was in a different context, but I had to do it, and I didn't know what we're about to talk about. So So it's confusing at first. You don't know lambda and you don't know x. And how do you solve it for x and lambda? Okay. So, and the key to solving it is to write it down as this equation. And here's why this is helpful. Now we're going to rely on all the homework that we did. What does it mean to solve some matrix? Okay, so Simpson's clause. Some matrix times x equals 0. What is the system of equations called again? Forgot. X equals 0, we'll call this.
Was it the non-trivial solution?
There's homogeneous, exactly that's what I'm after. It's called a homogeneous system. Again, it's not important to, so yeah, maybe it was not a fair question, but it's a homogeneous system of equations, right? Mx equals 0. And the question now becomes, because I am looking for non-zero x's, the non-zero x's, well, 0 always solves this system of equations. When I'm looking for eigenvectors, I'm looking for non-zero eigenvectors. 0 eigenvectors are of no interest to me. I'll ask you later why does it not even make sense to even consider 0 eigenvectors after we do a couple of examples. Why not consider a 0 eigenvector? Legitimate question. But for now, so by definition that we gave, the x's, the eigenvectors are non-zero by definition. So let's stick with that. Lambda, by the way, can be 0 or non-zero. There's nothing special about lambda eigenvalue being 0. But eigenvectors must be non-zero. Again, that was an aside. So, and here's the important question. So we're looking, as you've just suggested, for non-trivial solutions. Want non-trivial solutions. Want non-zero x's. X's that solve this. That solve this. That solve this. What this? This. Well, the role of matrix M here is played by the entire A minus lambda I. Well, after all, it's just some matrix, right? As we just saw here, it's some matrix. Okay, it's just some matrix. Where do we see it? Okay, but we'll see it again. Anyway, it's just some matrix. It's an n by n matrix. Okay, so when will, now we know how to solve systems of linear equations, Gaussian elimination. So I'm looking for a non-trivial solution. Suppose I do Gaussian elimination on it just to find it. Imagine that lambda is fixed for a second. So it's just some number. So this is just a matrix of numbers here. Again, a concrete example. With this example, we're continuing. So we'll see this in a second. Okay, so you do Gaussian elimination. You better end up with a row of zeros for me to have a non-trivial solution, right? So if I'm looking for non-trivial solutions, non-zero x's, I want to make this matrix singular. Agreed? Because it's only for singular matrices that I will have non-zero solutions. So let me write this down. It's a key point. Want A minus lambda I matrix to be, this is key point, to be singular or non-invertible. The same way, it's the same. Okay, so what's a singular matrix? Non-invertible, right? Want it to be singular. Now, a matrix is singular if and only if its determinant is 0, right? When a matrix has a 0 determinant, that's when you get that row of zeros in the Gaussian elimination. Okay, so we want the determinant of A minus lambda I to be equal to 0, because that's when A minus lambda I is singular or non-invertible, or when its Gaussian elimination leads to a row of zeros. All equivalent ways of saying that the matrix has that matrix times x equals 0 has a non-trivial solution, non-trivial x's, non-zero x's that solve it, right? So this determinant is a polynomial in degree, is a polynomial in lambda. Okay, lambda is the variable here. So others are entries. So I'm looking for those lambdas that make this determinant 0 in lambda. It's a polynomial in the called characteristic polynomial. Characteristic polynomial. Okay, so now for this concrete example, let's write it down. Okay, so for this example, again, we are here. Is what I wrote down, are there any questions about what I wrote down here? Any questions about what I wrote down? So now we'll go with the numbers themselves. So step one, we need to find those lambdas that make the determinant of this thing zero, this determinant zero. So compute that determinant and set it to zero and find out which lambdas make it zero. Find lambdas that make the characteristic polynomial zero. Lambdas that make this determinant zero. Because only for those lambdas will I have that times x equals zero will have a non-trivial solution. So let's see. Okay, maybe I'm talking too much. So find those lambdas. So let's write the determinant of this. Determinant of, this is my A, 1, 2, 5, 4. And once you do an example or two, you'll omit this step usually. Not this step, the step you'll do, but just writing it down. I just want to like write down it in a very detailed way. Minus lambda I. I want the determinant of this matrix to be zero. So again, this is the determinant of 1, 2, 5, 4 minus lambda these. And okay, and this is the same as the determinant. And let me subtract lambda there. This stays here. This is a 5. This is 4 minus lambda. So now I have a single matrix whose determinant I want to compute and set it to zero. So I want to see when is this determinant zero for which lambdas. Okay, so well, a little bit on a aside. So help me compute the determinant of this matrix. You should put this on the cheat sheet for 2 and by 3 matrices for your final. Because when you do those problems in eigenvalues, you need to compute this determinant that I have here right now. So, but the determinant of this matrix is what? Minus BC, right? Okay, why that's the case? Okay, let's talk about that later. But that's the determinant. That's how you compute the determinant. Okay, it's the parallelogram that's spanned by the columns AC and BD, but it's a nice geometric interpretation to this determinant. Anyway, okay, so let's continue. Now I have a formula on my cheat sheet. I didn't know it, but I brought it to the exam. So here's the determinant, turns out to be 1 minus lambda, that's my A, times my D, which is 4 minus lambda, minus C times D, which is 5 times 2. Okay, so that's my determinant. And this is the same as 1 times 4 here, minus 4 lambda. Maybe there is a, what is that, minus 4 lambda. Maybe there's minus 1 lambda here. Maybe there is a lambda squared, and this is a 10. Okay, so here's the characteristic polynomial. This is the same as lambda squared minus 5 lambda and minus 10 and 4. That gives me minus 6. Okay, this is for this matrix. This is the for this matrix. For this matrix, it's characteristic polynomial. This characteristic polynomial. Characteristic polynomial. Poly in level. Okay. Okay. Now, which lambdas make the determinant zero? We just computed the determinant. This is the determinant. Is the determinant of A minus lambda I, characteristic polynomial. That's how we define it. All right, so let's set it to zero and find which lambdas make it to zero. It's a quadratic equation in lambda. So just solve it. You remember that formula, minus B plus minus square root of B squared minus 4AC divided by 2A, all of that stuff. If you don't remember, you don't have to. I don't know why people remember this. Okay, but if you remember, that's great. If you don't remember, you bring it on the cheat sheet. So what we're solving is lambda squared minus 5 lambda minus 6 equals 0. And I'm not going to use that formula because here you can see, and you can bring the formula just in case you just have it. But lambda squared, I can just simply see it that this is well, if I make this minus 5 lambda, if I make it plus lambda and minus 6 lambda, right? Minus 6 equals 0. This is going to be lambda times lambda plus 1, and this is going to be 6 times lambda plus 1. Okay, admittedly, it's just a bit of algebra, but I'm looking for the roots of the polynomial. It's going to be lambda plus 1 times lambda minus 6 equals 0, from which I get the roots. Lambda 1 equals minus 1, and lambda 2 equals 6. These are the roots of the characteristic polynomial. These are the only two numbers that make the characteristic polynomial 0. If I were to plot this characteristic polynomial on the lambda axis, I'll get a parabola that crosses the lambda line in 2 spots. Okay, but anyway, long story short, you have 2 roots. Okay, this is going great. Okay, because now when I have these 2 roots, for each one, so let's check that the determinant, so we found those lambdas in such a way that that determinant of a minus lambda I would be 0. So let's take these roots one at a time, and for each one, compute the associated eigenvector. Because each, now we're in a lucky case, I'll tell you that we have 2 real roots, okay, of this characteristic polynomial, and they're distinct. And we'll later see why that's the nice case, but we're in a nice case. So it's a hand-selected matrix. So, but for each of these lambdas, let's start with the second one. You normally start with the first, but I'm going to start with the second one. And actually, let me call this one lambda 1. You normally, okay, there's some people who are sticklers for these conventions and make always the smaller of those 2 lambdas, make it the first one called lambda 1, but it doesn't matter to us. So I'm going to start with lambda 1 equals 6. Just to break the convention, just for the heck of it, I'm going to start with the bigger one. What's a minus lambda I? A minus lambda I, for this particular lambda, the first one, is, here's my matrix. Oh, I should have reminded you here that I'm still solving the same problem. Like this is the example that we have, or carried around. Okay, we're still working, we're just halfway through solving this example. So here's this is 1. Okay, let's write it down again in a detailed way. Usually we won't have to write this particular line. Minus 6 times the identity matrix, right? Usually omit this line, and you get right in there because this is 1 minus 6, 2, 5, 4 minus 6. This is a minus lambda matrix. Okay, so I'm going to have minus 5, 2, and 5 minus 2. Okay, so recall that it's important not to get lost in the trees. We're solving for what non-trivial x's make this 0. So this is my a minus lambda I. So the question is, we're looking for eigenvectors. So what x's, those will be the eigenvectors, what x's make this a 0? Those x's that solve this system of equations will be the eigenvectors associated with this particular eigenvalue 6. Now, my rows are multiples of one another. They better be, because that's how I selected the lambdas. I selected the lambdas so that the determinant of a minus lambda I would be 0, which means that the matrix is singular, which means that if I carry out the Gaussian elimination on that matrix because it's singular, I'll end up with a row of zeros. And of course, if I do one more step of Gaussian elimination in this matrix, will I not end up with a row of zeros? Please help me out. What's one step of Gaussian elimination here?
You would just do row 1 or row 2 plus row 1, and then it would just be 0, 0.
Yeah, and I agree with you, by the way. This row 2 is so. Let me write down just that row 2 that you suggested. Here's the single equation. So here I have 2 equations, but I'm writing down a single equation, just that equals 0. And that one, well, has a non-trivial solution because that's the way lambda equals 6 was selected. I better have a non-trivial solution. And of course I do. How many pivots and how many frees do I have? Which one is pivot and which one is free?
Your pivot would be -5, and then your free would be,
okay.
Or I guess in that case, your pivot would be 5,
yes.
your free would be -2.
Yes, everyone's on the same page, right? So here's the first guy is my pivot, the second one is free. So now I get to set free to 1 and figure out that the other guy then has to be 2/5. But instead of dealing with the fractions, I'm going to set now the pivot to 5, and the other guy will be 2. So x equals this x. 2, 5 solves the system. Is a solution, I should say a solution, because like 2050 is also a solution, right? Is a solution that we pick. So the eigenvector, associated with the eigenvalue lambda equals 6 is 2, 5. But that's just one of them. That's just one of them. I haven't yet. Now we need to compute. Now we need the eigenvector for the other lambda, which was -1. So now we're in this case, just as we were in the case here for lambda 1 equals 6. Now we're in this case of lambda 2 equals -1. Okay, with -1. So what's my matrix? Was 1, 2, 4, 5. 1, 2, was it 1, 2, 4, 5? 1, 2, 5, 4. 1, 2, 5, 4. So a minus this lambda I is, now I'm going to skip that step there that I did, minus 1. This is a minus lambda I'm writing down, 4 minus -1. And those off diagonal entries are always the same. Okay. Okay, so this is the same as 2, 2, 5, 5. I better have rows that are multiples of one another. The determinant of this matrix was lambda was selected so that the determinant was 0, so that I have multiple rows. So now I'm looking for the eigenvector. So what eigenvector solves this system of equations? This is the eigenvector, the one that solves this system of equations. Okay, so what do? How many equations do I have? Really equations that I need. One is the multiple of the others, redundant information.
You only have one equation.
Yeah, you only have one equation. In fact, if I can even divide it by 2, but let me not divide it by 2. Let me just write down the top equation. x1, x2, I only need 1 because the other gives me no new information. The solution to this system of equations is set one of the pivots to 1, the other is going to be -1. Right? So solution is x equals this x1, x2, that x. The solution is, well, actually, let's set that one to -1. This one will be 1, doesn't matter. I just picked one vector on that line. I could have picked 20 minus 20. That would have been an eigenvector. But I picked like something simple looking, whatever. So we're done with this example, finally. First, let's confirm the one that I told you about. Remember I told you that 6 was an eigenvalue and we found the eigenvector 2, 5 at the very start. So we found it now according to this procedure. And the way to write down answers to eigenvalue problems. So answer, lambda 1 equals 6 and lambda 2 equals -1 are the eigenvalues. And again, let me remark that people like sometimes to write down the smaller eigenvalue first, which I agree makes sense, but that's the way I wrote, that's fine. Our eigenvalues and the associated and each eigenvalue will have an associated eigenvector. For lambda 1 equals 6, the eigenvector is, let's call it V1, 2, 5. And for the other guy, the lambda equals -1, okay? For lambda equals -1, the eigenvector is -1, 1, or 1 minus 1, whatever. -1, 1, they're both eigenvectors. They're actually just so that I don't wave hands too much and don't say whatever, which would be not very appropriate. I want to put the eigenvector that we agreed upon, that we found. Okay, so that's the answer. That's the solution. Does that make sense? Okay, so this is great. This was a nice example.